Hi, this is Jeff Spence, your Math 135 instructor for the Community College of Denver. I'm doing a little lecture on probability, which is introduced in Chapter 5.1. Probability is a way of assigning a numerical value to an event due to uncertainty, like the chance that it might rain or the chance that we flip ahead or things like that. There's a lot of uncertainty out there due to randomness, and probability is a way of giving a numerical value to kind of give you an idea of how likely something is to occur. So to start off, we have experiments, okay, and I have a list of experiments here. And for each experiment, we have a sample space and an event. So let me go through these individually. If we have the easiest experiment would be to flip a coin. The sample space is the collection of all possible outcomes from that experiment. Well, if we flip a coin, we can either get a head or a tail. Pretty simple, right? So those are the possible outcomes. If we roll a die, the sample space is the numbers, is the numbers 1, 2, 3, 4, 5, 6. Six-sided die, or you can write 1 through 6. If we flip two coins, the sample space, you might have read this in the book, is actually we could get a head and then a head. We can get a head and then a tail. We could have got a tail and then a head or a head. Okay, so there's 4 outcomes in that sample space. If we record the next experiment, record the number of heads from 5 flips of a coin. Record the number of heads from 5 flips of a coin. Well, what's the minimum number of heads we can get from 5 flips? 0. What's the next number of heads we can get? 1, 2, 3, 4. And the maximum number of heads we can get from 5 flips is 5. So 0, 1, 2, 3, 4, 5. Now it's recording the number of heads. Same thing for tails, but sometimes we just focus on heads. And then last, if we wanted to record the number of people in line, say at a restaurant or at a cable place or at the registration line, for instance, the minimum number of people in line can be 0. We could have 1, 2, 3, and so on and so forth. We can have a bunch more, so I'm going to do ... We can have up to, really large number, probably not infinity, but a really large number. Then an event for each experiment in sample space is a collection, or it's either an outcome, like for flip a coin, an outcome is a head or a tail. So over there, an event, let's do, for flipping a coin would just be getting a head. That's an example of an event. I could have wrote tail. Rolling a die, an example event would be rolling a 1, or a 2, or a 3, or 4. We can sometimes say the event might be rolling an even, which is actually 3 numbers, 2, 4, and 6. So sometimes events can be collections of individual outcomes in the sample space. So what you see in the sample space in orange are all individual outcomes. An event can be one outcome or any collection of outcomes. So like an even is 2, 4, 6. The next sample space, flip 2 coins. I could say my event is to get a head, or to get both. Oops, I forgot to write. This should be tail. Excuse me. I don't know why I wrote that. My event could be to get both heads. Or my event could be to get at least one head. So that's head, tail, tail, head. At least one head. So each one of those 3 cases has at least one head. And then let's see here. Sample space. Record the number of heads from 5 flips. Sometimes we say, well, let's say we want 4 or 5 flips. That's an event. 4 or 5. Or we want an even number of heads. So that is 2 or 4, a different event. And then the last one that says record the number of people in line. Well, here's an event. At least one. What do I mean by at least one head? Or sorry, people in line. That would mean 1, 2, 3, and so on and so forth. At least one, so 1 and up. That could be an event. Now, from those sample spaces and outcomes, sample spaces, events, and outcomes, we have two main rules of probability. These are the rules that are going to come through for the rest of the course. This deserves its own page. It's so important. The first rule is that the probability of any event needs to be between 0 and 1. So if it could be equal to 0 or it could be equal to 1. If it's equal to 0, we say it's impossible or it hasn't happened yet. And if it's equal to 1, we say it's certain or has happened all the time. But a probability of any event needs to be between 0 and 1. That should make logical sense. And then the other one that's more interesting is actually that the sum of the probabilities, oops, I should have put S there, sum of the probabilities, i.e. S, but whatever, of all outcomes in a sample space equals 1. So if you go back to this sample space, heads and tails, for flipping a coin, the probability of a head is 1/2. The probability of a tail is 1/2. Add them together, you get 1. Same with rolling a die. The probability of rolling a 1 is 1/6. The probability for all the other numbers is also 1/6. So you take 1/6 plus 1/6 plus 1/6 plus 1/6 plus 1/6 plus 1/6 6 times, and you get 1. So this will always be the case that the sum of the probabilities always equals 1. This will be a useful tool for us when we figure out the probabilities of kind of events that are called complements, the not of something. Okay, from there now we move on to classical probability, which is a way of assigning probability without conducting an experiment. It's sometimes called theoretical probability, where you can come up with an expected outcome for a experiment without actually conducting the experiment. Now this works only when you can only use classical probability when the outcomes in a sample space are equally likely. Well, let's go back to the sample space, and the first three events, flipping a coin, getting a head or a tail, those are equally likely. Rolling a die, getting a 1, 2, 3, 4, 5, 6, those individual outcomes are equally likely. And if we flip two coins and record those outcomes, all those outcomes in there, head, 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 tail, tail, head, and tail, tail, have an outcome of 1/4. Now the next two, believe it or not, if we record the number of heads from 5 flips, the chance of getting 0 heads is not the same as getting 2 heads. You would probably expect getting 2 heads more than getting 0 heads, because 0 would mean that you'd have to get 5 tails in a row, which is not that likely. Same for number 5. So we can't use classical probability for 4 and 5. So I'm going to go back to this page, and the formula you have here is the probability of any event is the number, this n stands for the number of outcomes for that event, divided by the number of outcomes in the sample space. So let's look at this, those first three experiments. If we wanted to find the probability of getting a head, the numerator is the number of ways that event can happen in your sample space. Well, there's only one way we can get a head. Look at it, it's right there. There's the head. Okay, so there's one way to get a head out of 2 possible outcomes in the sample space, so it's 1/2 or 50%. Decimals or fractions or percents are all acceptable answers in this unit. Okay, probability of getting it even. Let's go back to the sample space. Remember, the probability of getting even, there's a 2, a 4, and a 6. 2, 4, 6. That is the number of ways that event can happen. That's the numerator. There's 3 ways that can happen out of 6. That's also 1/2 or 0.5. And then lastly, the probability of getting at least one head. Let's go back to that sample space. The sample space of getting at least one head is head, 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 tail, tail, head. That's 3 ways that can happen out of 4 total in the sample space, which is 0.75 or 75%. Now remember, we can only use classical probability for outcomes that are equally likely in the sample space. The next two sample spaces and experiments that I created, the outcomes are not equally likely, so we'll have to use some other formulas that we'll get later in the text. Like I said before, the classical method is not available for every experiment. Let's go back. The experiment of recording a number of heads from 5 flips or recording the number of people aligned. There's not a classical way to do that because we don't necessarily have a fixed number of outcomes in the sample space for like 5, so we don't have a number n necessarily. Or with 4, the outcomes aren't equally likely, so the chance of getting 0 heads, it's much less likely than getting 2 or 3 heads, and I hope that makes sense. So sometimes we have to use a different method of probability called the relative frequency method, and this is where you actually conduct an experiment. You actually do the experiment instead of like talking about flipping a coin or rolling a die without actually doing it. You actually do it and record the frequency, and you make a table. We've done this before, so if I was, we could in class talk about, how many heads we got, how many tails we got. Maybe we flipped a coin 100 times in the class, and the class total had a 45 heads and 55 tails. That would be the frequency. And then we could find the relative frequency. Since I'm keeping it simple here, it was out of 100 trials. The relative frequency would be 0.45 and 0.55. So we could say that for our class, the chance of rolling a head is 45% after 100 trials. We know that that's not necessarily the right answer because it's still flipping a coin, and we can use classical probability for that, but I'm just using a simple example where for any real probability thing, we can come up with categories, the outcomes in the sample space are the categories in the table, and then we can conduct this experiment ourselves and figure out the probability by dividing the frequency by n. We've already done this in 2.1 and 2.2 when you made your tables of where we're from and car ownership. And example 5.9 and on page 209 and 210 does a good job of kind of showing, like reiterating this point. So, from relative frequency, we'll move over to the law of large numbers. The law of large numbers states that if you are doing a relative frequency probability with running an experiment, that the relative frequency, in other words, the probability, but the relative frequency of an event approaches the true probability of that event as n approaches infinity. Another way of saying that is as n, the number of trials gets very large. So over a few hundred or in the thousands, if we run an experiment that many times, the probability, the relative frequency of that event from a table, like what we did here, we only flipped a coin 100 times, so that's why the probability isn't leveling off at 1/2 and 1/2. Notice that we flipped a coin here 100 times and got 45 heads. You would think, okay, well, that we're getting not very many heads in the first 100 flips, but eventually, if we flipped a coin 1,000 times, it would start to level off at 0.5 and 0.5 because we know the chance of getting a head is 0.5 and the chance of getting a tail is 0.5. So even 100 trials of an experiment is not really a large number. So we need the number of trials to get very large, beyond at least a few hundred. So this is shown in a diagram on page 208. I'll try and explain this diagram in my own way here. So let's say that we run an experiment where we flip a coin 6 times and we record the number of heads. So the sample space for that experiment, if we record the number of heads, we could get 0 heads, 1 head, 2 heads, 3 heads, 4 heads, 5 heads, and up to 6 heads, all 6 heads. So what I'm going to do is I'm just going to show you what this means, this law of large numbers means as we run just even 10 trials. So let's say in the first trial, trial number 1, I get 2 heads. Okay, so now on the first trial, we have 2 heads. So what that means on the frequency table, this up here is the frequency, this vertical axis is the frequency, and the horizontal axis is the trial number. On the first trial, we got 2 heads. So on the frequency diagram, I put a dot at 2. Right there. And on the relative frequency, 2 out of 6 is, we flipped the coin 6 times. 2 out of 6, sorry, is 1/3. So that's about right there. Okay? So they have the same, they're on the same spot. You could look at it versus relative frequency, or you can look at it versus frequency. The bottom one is relative frequency. Now remember, if you flip a coin 6 times, how many heads do you expect to get in the long run? Well, we would expect to get 3. And I'm going to draw a vertical line there on the graph. Okay, it's not perfect. Or we would expect to get a head half of the time, 0.5. That's the relative frequency. Well, the first time we got 2, so we're a little bit below expected. Next, on the second experiment, let's say we got 3 heads. Okay, so now we got, over the course of 2 trials, we have 3 heads. That puts us right there. And relative frequency, now you have to do relative frequency, we do 5 out of, we got 5 heads now out of 12 flips, so 5 out of 12 is just, it's approaching 0.5. And as we go on, let's start filling in more flips here. Let's say the next time we get, say, 5 heads, and then the next time we get 1 head, and maybe 0 heads, and then 5 heads again, and then 3 heads again. As we go on, now I'm going to sketch this because it's going to take me too long to do the rest. We should expect that, maybe sometimes it'll go above, the relative frequency, or the frequency might jump above. But eventually, as we go on with the experiment, the relative frequency or frequency of heads should generally start to approach the true probability of the event, which is either 3 out of 6 or 0.5. Okay, so I didn't finish the diagram, but that's basically what they're trying to explain on page 208. That as time goes on, as the number of trials increase, the probability, the relative frequency of getting number of heads should approach 50%, or getting 3 out of 6 in the long run. That's what this is, this kind of arrow going off to the right. Now remember, the 2 main rules of probability are right here. The probability of any event is between 0 and 1. And that if you sum up all the probabilities in a sample space, like if we look at these sample spaces and add them all up, it'll always equal 1. That goes for all sample spaces, regardless of whether the events have the outcomes in the sample space have equal probability. The first 3, the outcomes had equal probability, so we use classical probability. 4 and 5, the outcomes are not equal, so we have to use different formulas, either relative frequency or coming up with some different techniques to figure out the probability of getting, say, 0 heads from 5 flips. But this is your introduction to probability. Look out for the video on 5.2 and 5.3 coming in a few days.